We are Team 2 and we are giving our final presentation on analysis and redesign of a paint gun. The paint gun uses a compressed air to spray the paint particles with the help of atomized air to cover the larger areas with the nice finish. Our primary customers are the commercial painters who usually paint the larger area on continuous basis, whereas the secondary customers are non-professionals who occasionally paints the smaller area as comparatively. Our annual estimated demand is 310,000 and the estimated production volume is 75,000. This is our assembly CAD model of the paint gun, which indicates all the parts in it. This is the exploded view on the right hand side, which shows all the parts, and the left hand table indicates the part name and the quantity that we are gonna use in our model. This is our fast diagram which indicates about the primary function, that is the spray paint, and the secondary functions like direct paint, store paint, atomized paint, and the transport spray. This is our functional component mapping matrix, which indicates different parts and their utilities, where few of the components are forming groups like a trigger and adjustment nozzle to regulate the airflow and the minimum fatigue. These are our two main variants. The primary variant has the cup, which is used to fill the paint in it, and it does not have a adjustment nozzle, whereas the secondary variant has a hose which goes to the paint tank and it continuously gives the flow of the paint, and whereas it also has a adjustment nozzle which changes the shape of the spray. This is our product family design. On the left hand side, it shows the functional differentiation on a regulate sprayed and the store paint, whereas the right hand table indicates the component commonality. It shows the platforms and the modules that we are having in our model. This slide shows the product family assembly diagram. The first diagram has the different kind of branches, but after the modification done, it reduces the time and as well as the money for the assembly sequence.
The design for manual assembly analysis was completed by selecting the axle as a platform part and the paint cup as a module part. Our focus is on optimizing parts with high functional importance and high assembly time, which will be shown on the next slide. On the left side of the slide, the connection method for the paint cup to the main body of the spray gun was changed from a screw-on method to a snap-on method. This results in a reduced part count and implementation of snap fits. On the other side of the slide, the axle was combined with one of the E-clips. This resulted in a reduced part count and reduced fasteners. The implementation of a snap fit interface and the combination of the axle with one of the E-clips resulted in an improvement in the assembly time. The assembly time went from 84.66 seconds to 76.56 seconds. And the assembly efficiency went from 49.6% to 54.9%. After these changes were implemented, product functionality would remain unchanged and manufacturing costs would be reduced as a result of fewer total parts, decreased assembly time, and increased assembly efficiency.
In our design for automated assembly, we chose to analyze the trigger assembly, which consists of the main body, hanger, trigger, axle, washers, and snap rings. We chose this subassembly because it has high importance due to its functionality, but also high cost to assemble. In addition, the hanger has low importance, which led us to the decision of combining the hanger and main body before assembly. After completing the DFA, in which we combined the main body and hanger, as well as removed one of our snap rings, we found that there was about a 56% cost reduction for the total cost of assembly, as well as an improvement to the design efficiency. There were 5 main considerations that we took into account for our DFA. The first being DFA 1, which is reducing part count, and we did this by combining the separated hanger and main body parts into one manufactured part. The second was DFA 2, reducing fasteners, and we did this by removing one of our snap rings, made possible by a new axle design, which still ensures that the assembly is secure. The third was DFA 5, reducing part variety. Similar to DFA 1, by eliminating the hanger as a separate part type, we reduced the variety of parts that needed to be assembled. The fourth was DFA 10, adding features for easy insertion. And we did this by adding a groove to the axle, which allows for easy insertion and installation of the single snap ring. And likewise, for our final consideration, DFA 11, providing locating features. This groove on the axle serves as a positive locating feature for the snap ring.
The first process selection is on the paint cup redesigned as a snap fit. As it was made of PVC, a thermoplastic polymer, the compatible processes were machining, injection molding, blow molding, compression molding, rotational molding, thermoforming, and additive manufacturing. Only machining, injection molding, and additive manufacturing were capable with its circular shape. We selected 0.15 millimeters as its required tolerance since it needed to dependably snap into the paint gun base. The surface roughness is considered not critical since it has no impact on its function. When considering the economic batch size of 75,000, injection molding was the only remaining process.
On the termination of this process, we were able to carry out a manufacturing process cost analysis and determine a cost of $9.97 per part. The next step in our process was to plug the 3D model into DfM Pro. DfM Pro recommended a DIFM2 change in keeping the uniform wall thickness and a DFIM4 change of avoiding sharp corners. To accomplish this, we increased the fillet radius, which then gave us a manufacturing cost of $9.96 per part.
The next process selection was completed on the redesigned axle. Since it was made of aluminum, a non-ferrous metal, the compatible processes were sand casting, die casting, investment casting, centrifugal casting, forging, extrusion, sheet metalworking, powder methods, electromachining, machining, and additive manufacturing. All of these were compatible with its circular shape. We selected 0.05 millimeters as its required tolerance since it needed to dependably hold an E-clip on one end while being free to rotate in its intended cavity. The surface roughness is considered not critical since it has no impact on its function. With these factors in mind, machining was determined the only compatible manufacturing process.
After the DFA was completed and before the DFM was, for the new axle, a cost per part analysis was completed. The material cost per part was $0.005 and the operating cost was $0.017. The non-productive time was 22.031 seconds and the machining time was 4.372 seconds. The total cost per part was $0.445. After this was completed, the model was analyzed using DfM Pro. This recommended DFMC-10 and DFMC-13 changes, which is to provide fillets on the internal corners, as well as changing the diameter at the groove to maintain the length to diameter ratio. After the DfM Pro was completed and the changes were made, the cost per part analysis was then redone on the new updated part. The material and operating cost remained the same. However, the non-productive time and machining time were each about 2 seconds less. This resulted in a total cost per part of $0.383. Comparing the pre and post DFM of the axle, the analytical method gives a 14% or $0.062 price reduction per part. The hub's analysis and extrapolation gave a 9% increase or a $0.003 increase, which is possibly due to a more complex geometry on the filleted surfaces.
With this product, we could offer an additional service to maintain, refill, and refurbish used paint guns. This would include refillable paint cartridges, replacement parts, routine maintenance kits, and optional servicing or trade-ins. It would both increase customer experience and reduce costs by reducing downtime and extending product life. This applies to both professional users and DIY users. The service also provides environmental benefits, as less discarded units and waste will improve environmental health.
In conclusion, we were able to achieve our primary goal of reducing total part count, our secondary goal of making it easier to assemble, and our tertiary goal of manufacturing the parts at a cheaper cost. We improved our design for assembly by reducing the manual assembly time by 8 seconds and reducing the automatic assembly cost by nearly 56%. Our design for manufacturing reduced the cost of the manufacturing, the paint cup, and the axle by 0.1% and 14% respectively. Additionally, we would have liked to improve the ease of refilling the paint cup. Another approach we would have taken would be to explore modifying the spraying mechanism and reducing the sub-assemblies part count. Thank you for taking the time to review our presentation. We hope it was informative.